So this first thing that you picked up here says chi-square test. And this I just gave to you as it's a one-page little synopsis that goes over the purpose of the chi-square test and all the steps of it. And so as I go through today, I'm going to hit all these points. I'm not going to sit here and read this to you, so this is more of a reference sheet for you. And so I'm just going to kind of talk about these. So I'm introducing this chi-square test within genetics because data that is gathered from genetic experiments are conducive to using the chi-square test. The chi-square test tells you if your data is close enough to your expected results to tell you whether or not your data is acceptable or not. So like for instance, a genetics cross. You can, if you know the two parents, you have expected data. You can do a Punnett square and say, oh, I would expect in my offspring a 3-to-1 ratio. I would expect 3 times as many to have the dominant trait as the recessive trait. You have expected data there. So the chi-square test is useful for when you have data that you kind of know what you would expect. And then the second thing that's useful, the chi-square test can be useful for is when the data has categories. So that's usually the case in a genetics cross. For instance, when we do the Punnett square, and you have a 3-to-1 ratio, you'd expect 3 of them maybe to show the dominant trait, 1 of them should show the recessive trait. Those are your categories, kids that are dominant traits, kids that show the recessive trait. So for chi-square test, you have to have expected data and categories, which genetics crosses fit the bill, all right? So what this test does is say, okay, what if you do a cross and your expected data is 3-to-1, but you don't get exactly 3-to-1. You get like something a little off than 3-to-1. So the chi-square test tells you, is my data acceptable or not? Is it close enough to the 3-to-1 ratio, or is it so far off the 3-to-1 ratio that there's something wrong with the data? Either we did the experiment wrong, or maybe the parents weren't the genotypes that I thought that they were, and that's why I'm not getting the expected data. So there's some reason beyond that. All right, so that's the purpose of the chi-square test. So the second thing I want you to look at is the one that says using the chi-square test for statistical analysis of experimental data. All right, so that's this sheet here. We're going to work through this together. I'm going to use some examples to teach you how to use the chi-square test in analyzing genetic data. This third packet here, I'm going to have you keep till tomorrow. When I passed it out and set it out this morning, I had forgotten kind of about the shortened hours and things like that today due to the assembly. So we won't get to it, but we will get through this. So what I'd like you to do is take a minute and read through the first few paragraphs on the first page, and then there's table 7.3 below there. And after you read that, what I'd like you to do is see if you can fill in table 7.3 based on that the information that we talked about. So in looking at this, it tells you in the reading that we're looking at the cross, that we're crossing an F1 cross, and the parents are heterozygous. So big G, little g, cross with big G, little g, and it tells you in the reading that you would expect a 3-to-1 ratio. And where they get that is if you were to take the Punnett square by crossing the heterozygous individuals, this is what you would get in your expectations of what you would get. These three would show the dominant trait. This one would show the recessive trait. What's dominant and what's recessive according to this chart here? Green is dominant to albino, so you'd expect 3 green to 1 albino, so you'd expect that 3-to-1 ratio. As we said, that's what you expect. It's not necessarily what you get in your actual results when you cross these plants. And so in this data table, it's telling you what they actually got. So that's your observed. So they saw 72 green and 12 albino to give you a total of 84 kids. And so now you have this expected column, and you have to put some numbers in here as far as what you would expect. Can somebody raise their hand and tell me how you would figure out what goes in those boxes? Shane?
You apply the ratio to 84.
So you apply the ratio to 84. So tell me how you do that.
Like if it's a 3-to-1, which it is, so you could do like 3/4 of 84.
That's right, 3/4 of 84, all right, or 75% of 84. And so what do you get when you do that? 63, right? So there's 63. And then we can apply that same idea to the 12, or to the albino here. You'd expect 1/4 or 25% of them. So you take 1/4 of 84 or 25% of 84 and you get 21. And you should add this up and it should equal your total number that you had in your actual observed, which is what we get. All right, so we can see that our observed did deviate. It's different than our expected. So what this chi-square test is going to do is say, okay, we did not get exactly the 3-to-1 ratio. We didn't get exactly 63 and 21. But is it close enough to be due to just chance that we didn't get it, or is there something else at play? So one of the first things that we're going to do is look at how far it deviates here. So O minus E is observed minus expected. So since your observed is higher than your expected, when you subtract these, you get a positive number. So this is going to be 9. And then in the albino case, the expected is higher than our observed. So when we have observed minus expected, we get a -9. And so that's how much they deviated from the expected. And as it says underneath here, there is a small difference between the observed and expected, but the question is are these data close enough that the difference can be explained by random chance or variation in the sample, or is there something bigger at play that is influencing our results? So that's what the chi-square test is going to tell us. So if you flip your sheet over, I'm going to have you read through that page, and it's going to tell you a little bit about the chi-square formula and what the different things mean. And then there's another table, table 7.4, that I'd like to see if you can figure out. So at the top of the page, it gives you, talks about something called the Null Hypothesis. I want to explain something a little bit about that. So this is what it says at the top. It says that we use the chi-square test to test the validity of what we call a null hypothesis. And then in parentheses there, it tells you what the null hypothesis is. And that is, that's always going to be the kind of the same, that there's no statistically significant difference between the observed and the expected. And so that's your null hypothesis. It's always a negative. There's no statistically significant difference. So this means that in our example of this genetic problem, that there's no statistical significant difference between the number of observed and expected green and albino seeds here. So from that, we're going to use this chi-square test to see if we can accept or reject this null hypothesis, that if there is or isn't significant difference between our numbers, and therefore if we can accept this or not. So this is the chi-square formula. I wrote this out, what I just said. I don't think it's necessary that you write it, that there's no statistical difference between the number of observed and expected green and albino seedlings. That's how it would relate to this problem. So this is your chi-square formula. This formula, this is the chi-square, and this means the sum of, and then we take for each category the observed minus the expected squared and divided it by the expected, and we add these numbers together for every category that we have. And so this equation, you don't have to memorize. It's given to you for the AP test. You just need to know how to manipulate it. It tells you what each thing means. So this means the sum of, O is expected, or O is observed and E is expected, and so on. So you have to be able to just manipulate it. All right, so when you fill out this data table, this part right here to the 9 and -9 was exactly what we did on the previous page. So then we added to this, building step by step, you figuring out O minus E squared divided by E for each category. So we squared that, and so we get 81, which then takes away that negative. And then we divide that number in each category by the expected. So 81 divided by 63, I rounded to the hundredth spot, so it's 1.29. And then I forgot to tell you guys to round, or how to round. On the AP test, they'll tell you how to round. And 81 divided by your expected here is 21, and so you get 3.86. So this is where the sum of comes into play. So we did O minus E squared divided by E for each category. Then we add those together, and since I rounded off before I added them together, it came out to be 5.15. If you left it in your calculator and didn't round off, it would be 5.14, okay? And so either way, we're going to see that you get the same result. So this is called your chi-square number. So if you didn't round off, it's 5.14. So what do you do with this number? So how do we use this number to tell whether or not our hypothesis and therefore our data is acceptable or not? And we use what's called the critical values chart. And so that's what this down here is. And so this is table 7.5, which is below the other table. And so so I wrote a couple things on here. I want to explain how to use this table and how this table is valuable. So the first thing is this first column here is the probability or the p-value. And what that means is, I put here, you can think of it as the percent of time you would see similar results with your hypothesis. So they put them in decimal points, the probability. So 0.05, the p-value of 0.05, means that you would see those results when doing a cross between the big G, little g, you would see your results 5% of the time. 0.01 means that you'd see those same results only 1% of the time. 0.001 is 0.1% of the time. So why your row, the 0.05 row is highlighted, and I just outlined mine in green, is because that is the row that we want to meet. So in order to accept our data as acceptable, we want to see that data. If we were to redo the experiment, we should see that data greater than 5% of the time. If that data comes up less than 5% of the time, so like a 1% or 0.1%, then we're going to assume that it's not due to just chance, but there's something else that's skewing our data and why it's not exactly a 3-to-1 ratio. And so that's the row that is of interest to us. And so then the second thing in this chart is the degrees of freedom. And I wrote number of phenotypes in kids -1 because this is a genetics problem, but really for chi-square analysis, it's categorical data, so it's the number of categories you have, which for genetic problems, the number of categories is the number of phenotypes. So how many green versus how many albino do we have? So your number of categories, and then you -1. So we have 2 categories, green and albino kids. And so we take 2 minus 1, and then therefore for this particular cross, our degree of freedom is 1, which is why I circled 1 here. 1 is the degree of freedom for this cross. It isn't necessarily going to be the degree of freedom for another problem. All right, and so when looking at this, we're concerned about the 0.05 p-value, and our degree of freedom is 1. So where these meet, this number here is the number that's important to us, this 3.84. And so what we're going to do is take our chi-square number and compare it to this number 3.84. So if you look at here, kind of the trend in this chart, which this chart is much smaller for those people who have had stats or AP stats. You have a much bigger critical value table. This is what we'll see on the AP test if it's on there. It's a much smaller version, and it just gives you the part that is concerned with what the problems you'll see. And so in this particular case here, when you look at as we go down the chart, or as the probability of your data goes down, this chi-square critical value number goes up. And so if we look at our chi-square number, all right, our chi-square number is less or greater than 3.84. This is the number we want to meet. It's greater than that. And if you see here, 1%.
Interruption for a couple announcements. The pie in the faces tomorrow during all lunches. Pay $1, $3, or $5, depending on how close you are when you throw it. All proceeds go to charity. Also, the FCCLA will be selling carnations at all lunches this week. The cost is $1 for all, and all the proceeds go to Kids Against Hunger. Flowers will be delivered on Friday the 12th during 6 hours. And Spanish will be having their next meeting tomorrow after school at 3:43 for Valentine's Day festivities. And Decker Marketing students field trip forms are due Wednesday this week to attend the Frankenmuth presenters hospitality marketing presentation. Thank you.
All right, let me finish this real quick here. So what that means, our 5.15 is closer to the 1%, which means that our data, we would see less than 5% of the time. It'd be closer only 1% of the time. And so therefore, do you think we would accept or reject our? Reject. We would reject because it doesn't occur greater than 5% of the time. So you want your number to accept your data for this. Our number would have had to been less than 3.84. All right. So what I would like you to do, this is your homework, is if you go to the next page, at the top of it gives you what I just did in words, that it gives you 4 different points on how to use the critical values chart. That is for you for reference, but underneath there it goes to another example and a practice problem. So what I want you to do is try doing this with the practice problems in the rest of the packet for tomorrow. Okay? All right, that's it.